Hi and welcome to this video on integration. This one we're going to be looking at how the idea of definite integrals that we saw in the previous video is going to apply to the area under a curve. So what we're going to be doing is using our integral to calculate the area between the curve and the x-axis. So let's just have a look to begin with at the theory of what's kind of going on here. Now you definitely do need to be able to differentiate from first principles, i.e. come up with this idea of how differentiation works. You don't need to remember everything I'm going to be saying now and be able to repeat it in the exam, but they do expect you to have an awareness of what's going on. So here we go. Let's just have a little look at what's happening. So we've got the area to the left of our x-coordinate here. That area there is going to be called A, and it's a function of x, so it will change as x changes. So we've got a function of the area is a function of x. And so what we're going to say is, like, if we just increase x just a little bit, we get a small increase in the area. So what I've got here, this x coordinate here is x plus a small bit of extras, and that small bit of extras gives us this pink shape here. And now we're going to use this idea that we saw in differentiation about this idea of kind of tending to zero, i.e. we're going to make this small increase, this distance here, we're going to make it really small. And the point I'm making here is that at the moment, this shape here looks kind of like, well, it is essentially a trapezium, but as dx tends to 0, essentially this bit moves in closer, and essentially what will happen is it becomes rectangular. So what you end up with is a rectangle. Imagine we've got this incredibly small dimension here, and we've got, so dA becomes this rectangular shape. And if we wanted to work out the area of the rectangle, base times height, and clearly the height is the y-coordinate. So what we've got now is the area, this small increase in area, is the y-coordinate times by that small distance there, dx. Now, what we're going to do now is just a little bit of rearranging. So take the dx over there. So we've got dA over dx equals y. And now this next bit is just essentially just a little bit of notation as much as anything else. But as dx tends to 0, dA dx becomes, well, sorry, delta A, delta x is what I should have been saying, becomes dA dx equals y. And this equation here, this is the key. Because if dA dx equals y, what I'm now going to do is integrate this whole thing. So if I integrate dA dx, well, think about it, if integrate dy dx, you get y. So I'm going to integrate this side. So that dA dx becomes a, and over this side we've got the integral of y. So what we end up with is our equation here, when you integrate both sides, becomes that thing there. So you can see that in order to work out the area under the curve, basically what we've got to do is integrate. So here we go. So what we've got is the area under the curve between two coordinates, and the definition that we're going to get is that, so the area between the curve between the x-axis and the lines x equals a, that one there, and x equals b, is that x equals the integral between b and a, between limits of y dx. And that's our definite integral that we've seen previously. Now, essentially what's going on is, remember in the last slide we talked about this incredibly tiny or thin width little rectangle that was dA. This symbol here, this sigma, is like, so sorry, this integral symbol comes from this kind of the sigma symbol, which means summation. So basically, essentially what we're doing is adding up loads and loads and loads, technically an infinite amount of incredibly narrow rectangles. So all these tiny little rectangles, imagine splitting this area into an infinite number of incredibly tiny thin slice of rectangles. Add them all up, and that's where we get our integral from. So that's basically what we're doing. And it's this idea here that is the crux of what might pop up if they're feeling a bit fruity and fancy testing your understanding of where integration comes from in the exam. Now, let's just kind of finally delve into the last little bit, which is this idea of, well, how are we getting this between these two limits? Well, we said that the integral that we looked at last was everything to the left of here. So what we've got is this blue bit here, which I've now shaded, which is the integral between b and 0. So everything from our line x equals b down to there is going to be given by this thing here, this expression. And you probably guessed what's happening. The purple bit now, that's the integral between a and 0. And clearly this blue bit that we're left with here, the area that we're interested in, is just the difference between those two areas. It's all of that stuff. Take off the purple stuff, and that's why you've got a subtraction when you're evaluating a definite integral. Right, that's all the theory sorted. Let's have a look at what happens in practice. So we've got a question here saying find the area enclosed by the x-axis and the curve y equals 6 plus x minus x squared. So the first thing we've got to do is say, well, if it's enclosed by the x-axis and curve, we need to figure out where the curve cuts through the x-axis. So that's stuff we've been doing since the start of the course. So we're just going to put in y equals 0, do a bit of solving. So we've got orange colour, and there's a sketch. So basically what we're doing is finding the area between the points 3 and minus 2. So the area under the curve, this whole blue bit here between those two limits there. Okay, so we're going to integrate between the two limits. So what we're going to do is our integrating. There appears our square bracket again. There's our two limits. Plug in the values. So this one here is when x is 3, this one when x is minus 2, and again making sure you're showing that clearly, because your calculator will actually do this bit for you, but the method mark is for showing that intention to subtract, as I keep saying. And so we end up with that subtraction there. And again, be a little bit careful because we've got minus a minus there. So the area under the curve in this particular case is 125 over 6 units squared.